So if you look at those equations, so I just sorted them in this order, just to recapture everything. We have a certain general partial differential equation of second order with those coefficients. Then we want to bring it into a canonic form, which is this form. So we want to cancel out A and C. Therefore, we're going to need, so we're not needing the separation approach. Therefore, we need to introduce new coordinates in terms of x and y with new derivations in terms of x and y. And then I want to sort those derivations in terms of the new resulting derivations in order to get new coefficients a hat xi psi u xi psi plus b hat u psi eta plus c hat eta eta u eta eta. And then after that, these coefficients we will see, because of symmetric relations of these two differential operation operators, we will get the A and C hat will roughly look the same, will be the same. That means if we want to cancel out one of these or these, both will cancel out, but I'm going to show you. So before that I sorted everything here, so I just plugged it in here, and it takes too long, so I just wrote it down for you. Okay, so after that I sorted everything, and then we will see, okay, that's our new, I'm gonna color that will be, that's too much colors though, let me go with green again. So that will give us the new A hat in terms of psi eta, and this one will be C hat of psi eta, and the one in the middle will be B. But since I told you that A hat and C hat will look the same, but for the moment it does not, but it is actually the same. So what you can see is these are new coefficients, but we want to cancel them out. So this one only depends from psi x and psi y, and this one only depends from eta x and eta y. But actually it's the same. So if we want to, it's the same, how can I say, so we have the same coefficients for both of these new coefficients, because you see A, B, C, A, B, C, and the only difference is your argument plugged into this coefficient is different, but it's the same coefficient, because if you want to cancel this out, we need the zeros of this coefficient. So what we are going to do is this must be 0 and C must be 0, but the zeros will be the same because you have the same coefficients for both new coefficients. So it's actually sufficient to just solve one of these coefficients, and then obviously it is a quadratic equation. One is a quadratic equation in terms of x or y, or let us easier say you're gonna divide cx and c by cy, and that will be your first argument. It's easier to solve this equation. So, and the same, the other argument for eta x and eta y will be, you can name it v or something, but I will just say that it's actually the same. These functions will be the same, and the zeros of this function will just give you a certain value for that. Let us call this value lambda for x, y, but you will have two, so let me say lambda 1, and it doesn't matter if you're solving in terms of u or v, because the zeros, the value of those zeros will be the same, as it is the same function, but just another name for the argument. But with this substitution, we'll see, you see that it's actually the same function. So you will have lambda 1 equals, either lambda 1 will equal lambda, like our u, or lambda 2 will equal our u. So, because you see, or you can also, if you solve c, so that will give you, if you solve a, and c will give you the same, so you can call that u1, v1, and that will be u2, and lambda 2. So why do we need this? We need that because if you see, that's actually not that important. Oh, there was a small error. There should be 2 though, but the right hand side is not important. What is important is this value will give you a partial differential equation of first order in order to define n from x, y. Same counts for psi of x, y, and as you have two coordinates and two different values, that will actually be the key to first solve. For example, you take the first value and solve the first partial differential equation in order to get eta xy, and the second value to solve the partial differential equation in order to solve eta xy. How do you get the value again? So let me rewrite this function. For example, you have a, b, c, okay? You will have a hat will be a function of psi and eta, which is, sorry, not psi, yeah, actually of the derivation of them. So, okay, let me quickly see, yes, that's it, okay, because you see the other derivatives xi yy and eta yy will be all on the right hand side in the first order term, because if you have second order derivatives, you will have everything on the right side, as you might see here. If you look at this term, eta yy and eta xx, same for psi yy and psi xx. It's only depending of the operator, the differential operator of first order. So if you ask yourself that question, which is not important, so we have a function a x squared, xi x, a times psi x squared plus b times psi x psi y plus c psi y. Okay, as you can see here, you can do that by your own if you're a bit confused by the derivation of this function, but as I told you, it's just plugging in those derivations again. So I'm just plugging in those derivations to these coefficients. Then I'm sorting all the new functions, xi, eta, and eta, u eta. In this case, z eta. Here, and here. It's all sorted. And then I'm solving this equation again. So why is this a quadratic equation? Because what we can do is we divide by ey. So we will see that this is only a equation of one argument, which will be divide by y squared. So we will have xi y. This doesn't look so nice, but Greek letters, but different than Latin letters. So and here we'll get c, and then we want this coefficient to vanish, because we can divide it, because it's we want the right side to be 0. So that means we will just have to solve a function au. Let us name this term u, and then we will solve bu plus c, which is actually school math. Okay, that will give us values for u1, 2, lambda values, the one here above, and this lambda value will be the same whether if you call it u or v. That's what I wanted to show here, because the lambda values will be the same, and that means that our new partial differential equation of first order, which you can see here, will fulfill this and these values as well for psi, like for eta and for psi. The partial differential equation will fulfill both values because it's the same coefficients or same function, whether if it's u or v. Okay, and then we will have u1, 2 is b squared plus excuse me, I'm getting confused now. So it's minus b plus minus b squared minus 4ac divided by 2a. Okay, and as I told you beginning, a could be a function of x, y, but this shouldn't be too complicated, because I don't want to make it too complicated. Let's assume that for the beginning, it is just a constant term, like just a. But if it would be a function of axy, then a again would be a function of xi and eta, and you should plug in here all that here, but that would be too complicated. So let's just assume that you will get, in terms of this equation, you will get lambda terms which are constant, which can depend on psi eta. So you get lambda 1 and lambda 2, which can depend on psi eta, but I don't want to make it too complicated. And this will give you the values to solve the equation. But let us just assume, as I told you, so this is just the principle that this is just a constant and another constant, so that you can get the principle. Okay. Assume. It doesn't have to be, but it's just that you understand it better. Okay. What does that mean? So that means, okay, our u1 or our lambda 1 has to be equal to u1. So we have to have one u which fulfills, well, actually our u have to fulfill this in order to vanish. So means, oh no, we will have this. Okay, all our psi's and ethers have to fulfill this equation, so that a hat will always vanish. Yeah, in order to vanish all the time, we have to have such functions. The same is valid for eta. Sorry. Okay, and that's actually a really easy partial differential equation. So you might see this if you solve it. Okay, so I'm gonna show you how to solve the first psi, and then the same will be possible to for you name it, for eta. Yeah. Okay. And that's actually just a normal first order problem, which you can solve by a characteristical method. That's why all of this is called characteristical method. And you will name, so lambda 1, let me write that down again. You will have lambda x plus lambda 1 equals 0. And how can you solve that? Okay, you have the chain rule. As I told you, you will look on all the solution on one curve. If you have the x, y, x, y plane and z plane, you look on all the solutions on one curve, and then if that's your solution space, you will kind of project that onto your solution space and then expand your solution in that space. Okay, that means we can use the multi-dimensional chain rule in here, which gives us this equation, our characteristic equation, which would mean, the first coefficient. So here we have dx ds equals 1, because we have the coefficient 1. Then dy ds has to equal lambda 1, and because we have lambda 1 here, and then all the function z of s has to be 0, because the right hand side is 0 here. And then which is actually just the equation. If you look everything in one dimension, that would be multi-dimensional chain rule is the z of x this is a vector, and then all of this times. Okay, let me rewrite that. So z of s will be z x z y in a vector times dx of s times dy of s. Alright, and yeah, this means that all that s has to be constant in R space. So that's kind of, in this case, if the right hand